Now in doing this problem, I know that I need to use this same formula, this A of t equals, because I am changing by a certain percent every single year. Anytime we are repeatedly changing by the same percent, I'm going to be using this formula. Now I know that this formula typically tells us how much money we're going to get. And this is talking about wolves. It still applies. We can still go ahead and use the same formula to tell us what's going to be going on. So when I start plugging everything in, we should be looking at this as our first formula. Notice, A of t is 3,000. That's because I want to end at 3,000 here. I'm starting with 5,000, so that's my p-value, my principal. It's 1, but notice it's minus 0.08. That is because we're told that we're decreasing our population. Remember, to decrease, that's like our rate is negative, so instead of writing plus and negative, we just write minus there. And of course, to the power of t, it's still a t because that's what we're trying to solve for. All right, from here, it's a matter of doing the calculations. First thing I always like to do is do the addition or subtraction that's inside the parentheses, get that number, and then I can go ahead and get rid of anything that's not in the exponent. So in this case, that's going to be the 5,000. So I divide both sides by 5,000, and luckily with this one, all of our decimals are nice, easily written numbers. We aren't ending up with any of those irrational numbers or really hard to write ones. They require us to be a little fancy with the calculator, although we still have to be able to handle those. In this case, we now change this, since I'm solving for the exponent, into log form. Remember, that's the entire reason logarithms exist. They exist to solve for the exponent. And so we write in log form, then we calculate the value of that logarithm, use the change of base formula. You should get an answer here of about 6.13 years. Now, as you take a look at this, you'll notice the work that I'm showing. This is the level of work that I'd like to see on your paper as well. I'm noticing some of you are starting to get comfortable enough where you're starting to skip some steps. One step that I often see people skip is this one. A lot of people will see this and try to then just go straight to this. It tends to create certain potential issues. As soon as I start maybe switching the sides about what's on which side, we start getting things mixed up. And so actually write those steps in there. And so write out what it is in log form and then write your change of base. And that way you keep straight about what's going where much, much more reliably. All right, that problem being done, we're going to shift gears a little bit today. So far, every single problem that we have worked with these compounding interest kind of problems where we're changing by a certain percent, they've all been changing by that same percent annually. These have all been annually compounding interest problems. That is, nothing changes about the value until the very last day of the year, and then all of a sudden the value changes noticeably. That tends not to be what's really happening though, like with our wolf problem here. It's not like we have 5,000 wolves the first year until December 31st rolls around, and then all of a sudden we have like 100 less or whatever it is. So there's other ways that we can model these situations that can be a little bit more useful for telling us what's happening in the little details as well. Plus, financially speaking, a lot of transactions actually happen compounding maybe more like monthly. Like if you have a bank account that's actually earning some interest, like a savings account, they give you your interest once a month. That's compounding monthly. And so we're going to look and we're going to see what happens. But how do we do that in the formula? If we're not compounding annually, what's going to be changing about the actual math behind it? The good news is that you're actually really close already to knowing the formula, but we got to add a little bit into it. We're going to be using this formula. Now, before we talk about it, though, write it into your notes, and then we'll explain kind of what all this is telling us. All right, so you notice that a lot of the structure in this is very familiar. In fact, all the stuff that was printed there in black is the same as what the old formula was that we already knew, the same one we were using at the start of class. The difference is those n's that have been dropped into the equation. Now, what this is really saying is that I'm going to be taking whatever my rate is, and I'm going to be cutting it up into little bite-sized pieces. Like, if, let's say, we compound our interest twice a year, so we do it every 6 months, that would mean that I'd be taking my rate and I'd be dividing it by 2. So I'm getting half of the rate 6 months in, and then I'm getting half of the rate after another 6 months. But because my rate is then lower, I have to compound it more times. So then, like in that particular example of compounding twice a year, I'd be compounding it twice as many times, so it would be 2 times the number of years. And so we're compounding a smaller rate more times. And we'll get to see what kind of effect that has in the long run. One other little note, though, before we do. Notice here where it says number of times to compound the interest per t. That's just saying whatever t is measured in. Almost always, though, t is going to be measured in years. And that could be worth noting here. Now, this is basically the same equation with those n's thrown in. Actually, I would dare to say that this is the same equation. It's just that whenever we've seen this equation used before, we are looking at one particular scenario. When we compound the interest annually, what's the value of n? 1, because we're compounding it once a year. Notice, if n is 1, this is just r. And if n is 1, this is just t. Hence, the exact same equation as what we've been using before. This is just a souped-up version that we didn't deal with before. All right, now, we're going to be going through an example about how to do that particular equation with this. So start by writing down this problem. So then as we jump into the math, you'll have it already written down, and you'll have something to connect the formulas and all that to. Now, I know some of you look at this and you start thinking, but I don't want to write all of that stuff. Well, you can shorthand some of these things as we write them down on your paper, but let's make sure that you know what you can and can't shorthand out of this. You invest $1,000 in a savings account, so we don't need to actually write down that it's a savings account. We don't need to write down that it's an investment, but we do have to write down the fact that it's $1,000. That's going to be critical. It's a savings account that pays 1.2% per year. Now, it's tempting to think all you have to write down is 1.2%. But because we're now changing the time frames here, it's going to matter to say that it's 1.2% per year. Because you'll notice the next thing is interest is compounded monthly. You need to write down that it's compounded monthly. Sometimes you'll be told that it's 1.2% per month. That would change how we handle the situation. So we need to know that that interest rate is per year, but that we're compounding monthly. And what will the value of the account be in 5 years? So you'd also need to write down the 5 years in order to have a complete picture about what's going on and for this to actually be useful to you when you look back in your notes at it. All right, now, how do we know what formula to use? First of all, it is changing by a given percent. That tells me that I got to use the formula that we've been using. But how do I know whether it's the first one or the new one? Well, first of all, the new one always works. It's the same one as the old one, so you could have just plugged one in for n before. That would have been okay. But we also know that we actually have to use the new one because it's compounded monthly, not annually. And so we know we're going to be using this formula. Now it's just a matter of how do I put all the pieces together in order to be able to use it. Well, a lot of it's very familiar, of course. So A of t, that's our final amount. We don't know that. That's what we're going to be trying to find. So it's going to be A of, do I know what t is in this problem? Yes, we're looking to see what happens after 5 years. So I plug the 5 in there. Equals P, that's our principal. We know that is 1,000. Times 1 plus R. What's R going to be here? Yep. Remember, I have to take my 1.2% and I have to write it as a decimal. I have to write it as a number here. So I divide it by 100. And so that's actually going to give me 0.012. That's my actual R value. Wherever I see R appear, that's the number that goes into it. Over N. What's N going to be here? Well, remember, N is how many times does it compound per year? Here we are compounding monthly. How many months are there in the year?
12.
So it's got to be a 12. That's how we know. And so if N is 12, then when I get up into the exponent, I got a 12 there as well. It's 12 times T. T is 5. We now have our equation. Now that we have our equation, now it's just a matter of calculating and going through the actual calculations. Yes, have your calculator there. Be ready to do these calculations because I want to make sure you can get the right numbers out in the right places. All right, now when doing our calculations before, I would always start by doing this stuff inside the parentheses because order of operations says does parentheses first. And that's still going to be the case. But now when I am going to be adding inside the parentheses, I have to do the division before I can add them. Because that's also inside the parentheses. So I'm going to do 0.012 divided by 12. Well, that's going to give me 0.001. For this first example, I chose something that was actually going to give us a nice, pretty number there. You're going to see the numbers get a little bit uglier later. And then I add the 1 to that to get 1.001. And that's got to be to the power of 12 times 5. What is 12 times 5? 60. So I go ahead and write that line down so I can keep track of what I'm plugging in where. Now this looks just like the previous problems we've done, right? Just the decimal's a little smaller and the exponent's a little bigger, but still just typing it in. So I'm going to do the 1.001 to the power of 60. Take that number times 1,000. If all goes well, you should be getting an answer here of $1,061.80. And so you'll notice what was happening here is I took my 1.2% and I cut it up into 12 pieces. That was basically 0.1% each month. So this was paying us 0.1% interest every single month. But that meant that I needed to know how many months there were. 12 months per year for 5 years. That's why we got the 60 up here. It actually represented 60 months that we were compounding it. Now, what effect does the compounding monthly, though, actually have on the value? Was this a good thing for us or a bad thing for us? We could repeat the calculation just if it was annually compounding interest. If we did it for annually compounding interest, using the formula we had before today, we would have gotten 1,061.46. It's pretty close to the same thing, but it's not the same. Which one's bigger? The compounding monthly. So by compounding monthly instead of annually, we ended up with more money in our account. That's a good thing for us. Now, why is that? If we compound yearly from January 1st to December 30th, we have the same $1,000 in our account that first year. And then we get 1.2% of that at the very end of the year. But if we compound it monthly, January 31st rolls around and I get a little bit of interest. So then throughout February, the second month, I'm earning interest on that little bit of interest that I already earned in January. And so then I'm earning a little bit of interest on that interest as well when March rolls around. And so every month I'm earning interest on the interest. And so we start that compounding process earlier. And so compounding more often is actually in our best interest. It's to our benefit if it is in fact compounding more often. And one other note I'll give, this particular example, it's a savings account that pays 1.2%. Yeah, it's pretty good for a savings account, but it's still pretty low percent. That's actually the reason why the difference between these two numbers is so small. We're going to be doing some more examples with these. Not surprising, right? And you're going to see that sometimes this difference is actually going to make a big difference. So let's take a look at one more. please write down this problem and then set up your equation. When we go to set this one up, this is all the stuff that we knew from before, what went where. But there's one thing that, of course, is new here, our n value. In this case, we are compounding daily. Well, how many times then are we going to be compounding our interest every single year?
365.
The number of days in the year, yeah, so 365. And so when you set up your equation, this is what you should be looking at. Make sure that's correct on your paper, and then we got to look at the calculations, because the calculations with this one get a little bit trickier. The first thing I do, of course, is I have to figure out what the inside the parentheses equal. But in order to do that, I have to do this division first. Well, of course, you break out the calculator, you do 0.06 divided by 365 plus 1. But when we do that, we get a big, long, ugly decimal. We don't get a nice, tidy decimal like we did the first time. And this is going to be fairly typical here. There's not a lot of numbers that work out really cleanly when you divide them by 365, or even bigger numbers that you're going to be seeing later. And so what the key with these is of course, keeping that number up on your calculator. All right. So the way that I do these is I actually start by writing down, okay, I'm going to do 200 times, I leave a space for it, and then I do this number. I do the 365 times 20 to get the 7,300. And then I do the calculation in the middle, because I know that the next thing I'm going to be doing is the number to the power of 7,300. It saves me from having to type it in all over again. And so, on your calculator, when you do this problem, this number should be showing. Not because you typed it in, but because you just did this. The 1 plus the 0.06 divided by 365. Then you're going to say that number, that decimal, to the power of 7,300 equals. Then times 200. If all has gone well, this is what you should be getting. 663.96. Or in other words, $663.96. As you do those calculations, of course it depends on your particular calculator that you're using. The scientific works great that way. If you are on a graphing calculator though, yes, remember the answer key. Because like you can do this calculation to get that, and then you can just type it in from there. You can say 200 times answer to the power of 7,300, or on a few of your calculators even, it lets you just type whatever you want into the exponent without extra parentheses. You can even type it in the 365 times 20 there. But whichever method you're using, of course the key is that we get the right number out every single time, so make sure that you're able to get this, the 663.96, for that particular problem. We're next going to be dealing with this situation. Now, you can go ahead and write down the critical facts, yes, but process through what would each of these look like, at least. If you want to write them out, great, but at least think through each of these. All right, so looking at that first one, we start with $2,000. We're earning 10% interest per year, and our time is going to be 15 years. Now, what if we compound annually? Compounding annually, that's the stuff we could have done before today, right? That's just p times 1 plus r to the t. We don't even need the n in. And so you would have done 2,000 times 1.1 to the power of 15, and it gives us $8,354.50. Okay, fine. Monthly, same basic idea, except we need to put the n value in. What would n equal for monthly? Well, how many months are in the year? It's always how many of this appears in the year. And so, yes, it is going to be 12. Now, if I ran through that formula, this is what the work would end up looking like. And so you'll notice here that we went from annually to monthly, our amount increased again. But notice that with a bigger percent and a bigger time frame, the difference is much more noticeable, right? All right, now let's go one more step further. What about daily? Daily means that n equals what?
Depends on the year.
365, yes. Yeah, we're going to go ahead and ignore leap year for these. And if I do that calculation, then this is what I'm looking at. So notice, as I'm going down this list, every single one of these numbers is getting bigger. So the more often I'm compounding it, the bigger that gets. And it's by taking a number here that is always getting smaller and raising it to a power that's getting bigger. And it just happens that the way that this is balancing out, with the number getting smaller but still having a bigger power, we still end up with a somewhat bigger number every single time. Now the big question though, what about this concept here of continuously compounding interest? Continuously doesn't mean that it's compounding every day. It's more often than that. It's not even compounding every hour or every minute. It's not even compounding every second, because every second is still just at some particular time frame, and it's not happening continuously. There's still separation in those seconds. Continuously is like, yes, that n value is getting really, really big, but almost to the point where n would be like approaching infinity. What would happen if we went out to like put the biggest number humanly possible in for n and then go more? What would happen? Well, first of all, look at the way that these numbers are growing here. Would you expect, if I keep increasing n, would you expect this number to be like infinity? Would you expect it to be like billions or dollars or something like that? I'd expect it to be bigger, but how much bigger, I don't know there, because you'll notice that going from annually to monthly, it increased by, I don't know, like $550. Going from monthly to daily, it increased by, I don't know, like $50. So I would think that if I went down again, I'm not going to increase by like hundreds of thousands. I would expect to increase by a smaller amount. It's still increasing, but the differences are less and less as that n value gets insanely huge. And what ends up actually happening is that we are actually approaching a certain number. It's just that to find that number, some mathematicians had to go and do some extra fancy stuff. It had to do with infinite limits and what's it always approaching. And there actually is one particular number that kept coming up in those calculations all the time. It's one of those numbers that comes up often enough in math that they actually gave it its own name. It's E. And it turns out that this equation will actually tell us what will the value be if we get it down to compounding the interest continually. Add this to your notes, please. So first of all, you'll notice what E actually equals. It's this decimal. Now, it is an irrational number, though, so this is, of course, a rounded version. The irrational numbers, they go forever. They never repeat themselves. Kind of like what other irrational constant that you know very well? Pi. Yep. It's like pi. It's the same kind of number like pi is. It came up so often and ended up being so important that we gave it its own name. And so now we get to use E. And the first way that you can see it coming up was with continually compounding interest. Now you notice I underlined the word continually there. I would suggest you do the same in your notes, because that's what tells me that I need to use this formula. If I don't see that word continuously in a problem, I don't use this formula. If it's hourly, I use the other one that we got at the start of class. If it's compounding every second, I use the one that we learned earlier in the class. I just have to figure out how many seconds were in a year. Give you a hint, it's a lot. So you only use this when you see the word continuously in there. So it's for continuously compounding interest. Now, it's going to be P times e to the RT. Let's actually see how we can apply that to the problem that we were just looking at then. So in order to set up this equation, it does say continuously. And so I go ahead and start plugging this stuff in. Now it's A of t. Now I still know what t is. I still know it's 15. Equals p times, well, p is still 2,000. Nothing has changed to this point, but this is where things change. I need to put in now e. The good news is we have a symbol for it, so just use the symbol. You don't have to put in like the 2.7 and all that kind of stuff. Just use e, just like you use pi when you write equations. To the power of RT. Now what is R?
15. No, wait.
Remember that R is a decimal value. You still have to turn the percent into a decimal. So we do 10% divided by 100, it's 0.1. So we're going to do 0.1 times the time, which of course is 15. So we've got our equation. Now it's just a matter of actually doing the work and doing the calculation. Now the first thing about it is we want to know what this exponent actually equals. We have to do that first. So we're going to do 0.1 times 15. That just gives us 1.5. So now I have 2,000 times e to the 1.5. The next thing I need to do now in my calculator is I need to do e to the power of 1.5. So it's time to learn how to use your calculator for this purpose. All right, so depending on your calculator, the keystrokes feel slightly different. If you're on a graphing calculator, like a TI-83 or a TI-84, you're looking for a button that shows e to the power of x. That's the magic button that you want. Now, on the TI-83s and TI-84s, that's on the left side, third button up. It actually is right above a button that says LN. It's second LN. We'll be learning about the LN actually next week because it is related to e to the x. But you're going to go second LN. And when you do that on your TI-83 or 84, it then is displaying on the screen e to the power of fill in the blank. So you type in 1.5 and press equals, and then you say times 2,000. Now, if you're not doing this on such a graphing calculator, you're doing it on a scientific calculator. Remember when we did logarithms, you had to put the number in first? Same idea here. So, on a scientific calculator, the first thing you do is you type in 1.5, and then with that showing on the screen, you then are looking again for that button that says e to the power of x. And just like on the TI-83s and 84s, it's probably second ln. When you press that e to the x button, it then automatically does e to the power of whatever number you had showing. So the last thing is multiply it by the 2,000. Whichever counting calculator you're using, you should of course get the same answer, which is 8,963.38. Make sure you're able to get that correct answer out of your calculator.